Welcome back to a new video lesson on game theory. In this new pill, we will introduce the first way to predict a game, explaining some about the equilibrium dominance and the iterative duration of strictly dominant strategies, which is the easiest. Let's begin by talking about the concept of a game's solution. As we mentioned in previous videos, the two objectives of the game theory are, on one hand, to learn how to formalize and represent strategic situations in the form of a game, and secondly, to be able to predict which strategies will be played and therefore what the solution to each formalized situation will be. The concept of a game's solution depends on the type of game and on the information that each player has about the other players. If we have static games and complete information, we will use the Nash equilibrium, but if we have static games with incomplete information, we will use Bayesian equilibriums. On the other hand, if we have dynamic games with complete information, we will use the perfect subgame equilibriums. And finally, if we have dynamic games with incomplete information, we will use perfect Bayesian equilibriums. Let us now move on to consider how the players will act. The first concept we will study in this regard is that of strictly dominated strategies. We can use it to predict which strategies will not be played if rationality is common knowledge. Sometimes this information helps determine by elimination which strategies will be played. We say that one action of a player in a game dominates another action of that same player if the first provides always higher payoffs than the second for all likely combinations of the opponent's actions. We then say that the second action is a dominated action or a dominated strategy for this player. On the other hand, a weakly dominant strategy for a player in a game is that strategy that yields equal or higher payoffs than any of the other likely strategies, regardless of the combination of the opponent's strategies. In other words, a strategy of any player is strictly dominated by another if, no matter what the other players do, the second one always provides a higher payoff than the first. A rational player will never play a strictly dominated strategy because it can never be optimal. In the prisoner's dilemma that we will see in following videos, this means that no rational player will choose the strategy of cooperating. And since there are only two strategies, this in turn means that both players will choose not cooperating. In this game, therefore, we can predict exactly what will happen simply by using the concept of a strictly dominated strategy. Does this occur in other games? Sometimes yes, but in many other cases no. So we will need other ways to predict or to end the solution of the other ways of defining static games. One way, therefore, to find the solution of a game is to delete or eliminate all dominated strategies one by one, since they will never be played if the player is rational. In this way, the size of the game, the size of the matrix or the decision tree is reduced in any stage of the approach, simplifying it by narrowing down the number of likely strategies. We may reach a final situation in which only one non-dominated strategy remains for each player. Therefore, this will be the solution to this game. Let's look at another example where this can be applied. As in the case of the prisoner's dilemma previously commented, although in a much less direct way. Clearly, the strategy right of the column player is dominated in this case by the strategy center. If this player is rational, they will never play right. Now we have assumed that all players know that the others are rational, since the rationality of the players is common knowledge, as we previously commented in previous videos. Therefore, the row player can deduce that the column player will never play right. If that is the case, the only likely outcomes are that player 1 plays up or down, and player 2 plays left or center. In this situation, the down strategy is strictly dominated by up for player 1. Thus, the row player will not play down. We have also assumed that everyone knows that all players are rational. Consequently, the column player can deduce that the row player will not play down. Therefore, the best option for the column player is then to play center. We have thus arrived at a single predictions, up and center, using what is known as the iterative deletion of strictly dominated strategies. There are some problems or challenges associated with using the elimination or deletion of strictly dominated strategies to find the solution of a steady game. First, it's common knowledge that all players are rational, and it is a strong assumption or a strong hypothesis that in the real world we have many situations where players play not in a rational way. Very often this method has no solution. In the sample of the proposed matrix, only n for player 1 can be eliminated. So what then? However, there are countless games in which we cannot obtain a single prediction using dominance arguments, or there are many games in which we cannot obtain the final solution using the equilibrium dominance that we have shown in this video. Indeed, in many cases, no dominated strategies exist, as in the Battle of the Sexes, for example, or they are not enough to reach a unique prediction because after eliminating all dominated strategies, more than one combination of strategies remains for each player. That is why in later videos we will discuss other ways to predict a game's outcome and introduce, for example, the concept of Nash equilibrium in both pure and mixed strategies.